tests, and you did very well. I'll hand them back at the end of the class. Remember to stop 5 minutes early. Okay, any questions about anything before we go ahead? All right, so I mentioned we're going to talk about 4 tests: the Neyman-Pearson test, the Wald test, the integration test, and the permutation test. So we've done the Neyman-Pearson test, and we saw that's only for testing a simple hypothesis versus a simple alternative. Very restricted, but still an important test theoretically to understand. Now we're going to talk about the Wald test. And the Wald test is used for testing a scalar parameter so theta here is scalar. You want to test theta is equal to theta 0, typically versus theta is not equal to theta 0. And we're in this situation where we have an estimator which is asymptotically normal. Typically it's going to be the maximum likelihood. Although this test could be used more generally. And so the test statistic is very straightforward. The test statistic is simply the estimator minus the hypothesized value over the estimated standard error. Keep in mind that for the MLE, the estimated standard error is going to be 1 over root n assured information. So there's really kind of a root n. But what do we know about this test statistic under the null hypothesis? If H naught is true, then we have the estimator minus the true value over the standard error. We've seen that that's going to converge to. So, in other words, we're assuming we're in a situation where this central limit theorem holds, and then this just becomes like a normal random variable. And so the rule is to reject the null hypothesis if this is bigger than, I think there's a typo in the notes here, it should be bigger than z alpha over 2. Remember that for the two-sided alternative, you need to use alpha over 2. Why? Because we want the type 1 error to add up to alpha. But under the null, we can make a false rejection either if it's too big or too small. So alpha over 2 plus alpha over 2 is alpha, and that means that this critical value has to be z alpha over 2. So you can see why this is a useful test. It's very, very simple. Compute the statistic, reject it if it's bigger than this. Okay. So that's the Wald test. Actually, why don't we just take a moment to look at what the statistic looks like under the MLE and what happens under the alternative. So under the null, what is the distribution of this? Well, it's asymptotically normal 0, 1, right? So let's look at the statistic a little bit more closely. Let's write it out. When it's the MLE, this is so I want to make a couple of comments about this. First of all, in some textbooks, this standard error, instead of putting in the estimated parameter, some people put in the null value, which is perfectly acceptable because what we care about is to get the right type 1 error is what its behavior is under the null hypothesis. Under the null hypothesis, we actually know theta. It's theta 0. So you could put theta 0 there. On the other hand, you can also put the estimator because under the null hypothesis, theta hat will converge to the truth of theta 0. And so by Slutsky's theorem, you get the same limiting distribution. So you'll see it written 2 different ways, this Wald statistic. Some people, for the standard error, use the estimated standard error. Some people use the standard error under the null hypothesis. Either one is acceptable. Yes?
Is one of them to give
One of them give more power. That's a good question. We should think about that. I'm not sure. I think that, in fact, let's look at the power. So let's look at the, what is the behavior now under H1 of this statistic. So let's rewrite it. Here's our statistic. I'm going to rewrite it now. So this is again assuming that there's some true value theta which is different than theta 0. So I'm going to subtract and add the true value. This is not right. I hope everybody can see that I've got this incorrectly. This was a test. I've got the standard error upside down here, right? Here's the standard error. So let me just rewrite this properly. It'd be pretty weird to have the root n on the bottom. Now let's do it on the alternative. It's the same statistic, but I want to rewrite it a bit. Because I'm going to add and subtract the true value. So all I did is add and subtract theta here, where theta now is the true value, which is some number different from theta 0. Now this is a standardized statistic. This is the estimator minus the true value divided by the standard error. So this is converging to a standard normal. But we have this quantity. This is just converging by assuming the Fisher information is continuous by the continuous mapping theorem. This is converging to I of theta at the truth. But the dominant thing is this. They have theta minus theta 0. This is the true value. This is the null. We're assuming they're different, and it's getting multiplied by root n. So this is a big number. This is getting bigger and bigger as n goes to infinity. What we're getting is a normal plus something constant. So what's going to happen is under the alternative, it's going to be something like this. And of course, that has a high chance of being bigger than our cutoff point. That's showing you that the power is increasing in two different ways. As n gets bigger, the power increases, but also if the true value is far from the null, you get higher power. That all sort of makes intuitive sense. Yeah.
You mentioned using Slutsky's theorem, and the question is, was it only for multiplication and summation?
Yeah. So let's do it here. So let's suppose again that the null hypothesis is true. I can divide and multiply by this. And what we have now is this is converging to 1 in probability. And now I have root n, this times this, so I've got this divided by its correct standard deviation. So it's still, either way it converges to a normal zero.
But under the alternative, that would be right and
No, we don't test under the alternative, right? We don't know if the null or the alternative is true. We just do the test. Now the question is, how does it affect the power? Because you see, it hasn't affected the asymptotic type 1 error. But does it affect the power? The answer is not very much, right? Because if I had put theta 0 here, this would just converge to a number. It wouldn't be the correct Fisher information, but that doesn't affect the type 1 error. This is just a number. So if I put I of theta 0, I of theta, either way this is converging to a number. What's affecting the power is that this times this is getting big. So the answer is it doesn't affect the power very much.
Why did 2 root n's in the second?
Yeah, it's a typo. That's called a typo. That was not a magic power booster. That would have made power much bigger. Thank you. So the answer is under the null hypothesis, you'll get asymptotic type 1 error. That is the probability of a false rejection. The probability under theta 0 that you reject. Whether you use theta 0 or theta hat, it still converges to alpha. On the other hand, under the alternative, you can see the power goes to 1. Well, that's another typo. These are all on purpose. There's no mistakes. Any other questions about the wall test? Okay, so that's, if you're just testing a single parameter, you can see that's a very, very quick, easy test. Now we're going to do the likelihood ratio test. And the advantage of this test is you can test a vector as well as a, not just a scalar. So this is called the likelihood ratio test. So I want to test possibly a vector value thing, and it might now be in a set versus not. Let me clarify what I mean. Let's think about a normal. So in this case, the theta is mu sigma. Suppose I want to test mu is equal to 0. And there's two different ways to think about this. You could say, oh, that's a scalar, so I can do the wall test. Or I can think of it as a test of the whole vector, because when I say mu is 0, here's mu and sigma. You can also think of it as I'm testing whether the whole vector is in this linear subspace here, right? Mu equals to 0 corresponds to this vertical line. So in this particular case, I can either think of it as a test about a vector lying in a subspace, that the whole vector lies in this space where mu is equal to 0, or I can think about it as a scalar. But there are some cases when you can't do that. So in this case, we can do either the wall test or the one I'm about to show you, the likelihood ratio test. We have an option. But there are some situations, suppose theta was equal to theta 1, theta 2, theta 3, theta 4. And suppose I want to test whether theta 1 is equal to theta 2. That's my null hypothesis. Then that's really asking, I have a 4-dimensional vector, and actually let's make it even more interesting. Let's make it that theta 1 equals theta 2 equals 0. So what I'm doing is I'm taking a 4-dimensional parameter, and I'm making a null hypothesis that the first two parameters, say, are equal to 0. So this is going to be of this form. Theta 0 would correspond to all the 4 vectors where theta 1 and theta 2 are 0, and this would just correspond to the whole space. In that case, there's no simple scalar quantity that we can do a wall test on. So the point here is sometimes you're testing a scalar, sometimes you're testing that a vector lies in a set, sometimes it's both, sometimes it's only the second case. So we'll do some examples of that in a minute. But you can see that this is therefore more general than the wall test. And so we're going to write down the likelihood ratio test. You can think of it as sort of at least motivated intuitively by the Neyman Pearson test. The test statistic is going to be the following thing. So to have a picture in our mind, again, let's think about, I'll just draw a blob for the parameter space, like I often do. And then the null hypothesis is that this vector lies in some set, so I'm going to put that here as theta 0. It's typically, for this purposes of this test, it's typically a linear subspace, but just think of it as some set. So the null is that this parameter lies somewhere in here. And the test statistic, lambda, what we do is we take, so we have a likelihood function now, which is over the whole space. What we're going to do is take the maximum over the null. The maximum of the likelihood under the null hypothesis. Now the alternative is that it's outside of this, so I'm going to take the maximum outside that, but because this is just some very small set, the maximum over the alternative is the same as the maximum over the whole space, right? So excluding that line or a linear subspace in general doesn't change the maximum. Is that clear? And then I'm just going to actually take the supremum over the whole parameter space. I could take theta 0 complement, but assuming this is a continuous function and so on, you're going to get the same answer. So we're going to actually use the likelihood, the maximum likelihood over the whole space. That's our test statistic. Sort of like the Neyman Pearson test, except the Neyman Pearson test was only for a simple versus a simple. Now we have a composite null hypothesis and a composite alternative hypothesis. And intuitively, we would think if the null is true, this should be kind of big. But if the null is false, it should be small, so we're going to reject when this is small. Let's actually rewrite this. I'm going to write this as, what do I mean by this? I mean the value that maximizes the likelihood restricted to the null hypothesis. So I look at the likelihood along here and I find the maximum. That's just another way of writing the top. And the bottom is just the likelihood over the whole space. And so we reject H naught if lambda is less than C. And what we'll see shortly is, in general, that can be hard to do, to compute this. Sometimes you can compute the C, you get a size alpha test. Sometimes it's hard, but there's, as often, we can use a asymptotic approximation we're going to see that will make this very simple. And let me just, before we get to that, we'll spend some time on the likelihood ratio test. Let me make sure that at least the basic procedure is clear. Yes?
Can you phrase more precisely how do you take beta 0?
Beta 0?
In the, like, you don't take the complement, but you rather take
For what? This? The truth is, you should just think of this as the definition of the statistic. So I was trying to, yeah, in fact, you should just say, here's the definition of the likelihood ratio statistic. It's the sup of the likelihood over the null divided by the sup over the whole space. That's what gives us the correct statistic, so to speak. The only reason why I mentioned the other thing is a lot of people will say, why don't we take the sup over the just theta 0 complement? But in the sup, that's going to be the same because, you know, if I take the maximum of a function, and if I exclude one point, that doesn't change the supremum. So it's the same reasoning. But technically, it's actually defined to be, the denominator defined to be the sup over the whole space. So the part we're going to get to later is how, in general, we choose this constant to make sure we have a type 1 error alpha. We want to make sure that the probability of rejecting, the probability that theta is less than C, for all values under the null. Remember, to have a size alpha test, we have to make sure it doesn't matter which null value, anything in the null, we better make sure that the probability of rejecting is less than equal to alpha. So we have to choose C for this to be true. And we'll see, you can do this on a case-by-case basis. You could try to do it numerically somehow. Often, to make things simple, we'll just use a large sample approximation to make things easy. These large sample approximations, in principle, are never really necessary. We could numerically take every value of theta, figure out what C is, and make sure we have a C which works for every single thing. It would be a lot of work, but you could do it, and you would have an exact finite sample test. But we often just do the asymptotic approximation because it's quick and simple. But before we get to that, let's do a few examples of what the test actually looks like before we worry about the general situation. Any other questions about the definition of the test? So let's do a couple of examples. All right, let's start with the normal. So the data, let's say, are from a normal with mean theta variance 1, and I want to test theta 0 versus theta 0. Now, I could do the wall test here. But let's do the likelihood ratio test. This is a case where we can do either one. So, here we go. And what is lambda? So I have to take the likelihood, let's write down what the likelihood is for normal. The first thing is for the numerator, I have to find the maximum of this over the whole null distribution, over the whole null set. But of course, in this case, that consists of a single distribution, namely beta is equal to theta 0. So it's pretty easy. The likelihood under the null hypothesis is just this. It's just e to the minus n x bar theta 0. Now, the definition of the statistic is on the bottom, I put the likelihood evaluated at the overall MLE. So that's e to the minus n x bar minus theta hat. Well, what's theta hat here? It's x bar, right? So actually, this is just 1. So this is actually just so the test says I should reject. I reject. This chalk's not cooperating very much. Let's try this one. We reject if this is less than some constant, and all we know about this constant is we're going to choose it to make sure we have type 1 error alpha. But we are at liberty to rearrange this thing and just redefine the constant. And a little bit of algebra will show that rejecting when this is smaller than some constant is equivalent to rejecting when x bar minus theta 0 is bigger than some other constant. So this is equivalent to rejecting if x bar minus theta 0, in fact, I'm going to write it this way. And then is bigger than some other constant, let's call it c prime. Let's just rearrange it. Rejecting when this is small is the same as rejecting when this is big. And the reason why I wrote it this way is because this should look familiar. This is the Wald test. So it happens to be that the likelihood ratio test in this case can be rearranged to look exactly like the Wald test. And we know what this constant has to be then. It has to be z alpha over 2. So we have to reject when x bar minus theta 0 is bigger than z alpha over 2 in order to get a type 1 error at alpha. So what we've concluded here is that we can start with this likelihood ratio methodology, but eventually we have to say that we reject when that's small. By rearranging, that's the same as saying rejecting when this is big. The fact that it has to have size alpha tells us precisely what that constant has to be. So we've got this is the likelihood ratio test, size alpha, but that's exactly the same as the Wald test for size alpha. So in this case, they're exactly the same. Obviously, this is not always going to be the case, but in this case, they are the same. Okay, so let's continue to make it a bit more complicated by putting the variance in here. So now, I have this normal with a mean invariance, but I only want to test whether the mean is theta 0 versus the mean is not theta 0. Now, again, I have two approaches. The Wald test would say, what would the Wald test do? Well, first of all, I would find the MLE. How do I get the standard error? Well, this is a two-parameter problem. You have to get the Fisher information matrix. But you can get the standard error for theta hat. And then you would just do the Wald test. Theta hat minus theta 0 over standard error. And so on. But we can treat it as a likelihood ratio problem. Or as a likelihood ratio test. Because again, theta 0 is really, this is theta, and this is sigma. This 0. And theta 0 is really this, you can think of it as the set of all vectors, theta and sigma, in this set. So what's the likelihood ratio statistic? It's going to be the likelihood, and the way I would write this is, how do I maximize the likelihood over this set? So if I take the likelihood for a normal where both the mean and the variance are unknown, but now I tell you, you have to restrict the mean to be equal to theta 0. Well, that's just maximizing the likelihood over here. We're actually only maximizing over sigma with theta set equal to theta 0. In other words, you can write this as, let's call, this will just be theta 0, and it's the sigma that has to get maximized. Let's call it sigma naught squared of theta 0. I'll write it that way. To indicate it's the maximum of the likelihood for sigma, but when theta is taken to be known to be equal to theta 0. And that would be divided by just the overall MLE. Okay, now here's an interesting calculation to do, Once again, you know what this is. The formula is like this, and you know what the formula this is. You know what this is. You know what this is. This is not too hard to work out. It's just the usual sample variance, but instead of x bar, you have theta 0. So you plug it all in, you're going to get a big mess. E to something. We want to reject when that's small. But again, if you rearrange it, you will see that's equivalent to rejecting when the following quantity is big. S here. Okay, so this is actually, once again, the wall statistic. Why? Because this is the MLE minus the null, and then if you take the Fisher information and then you have to put in an estimate of the Fisher information, you're going to see you get this. This is just, in other words, the standard error of x bar we know is sigma squared over n. And so an estimate of the standard error, this is s squared over n. So again, we have kind of a walled statistic, and you will reject however, there's a big however here. If you look at most textbooks, when they do this test, they make two changes. They usually use the 1 over n minus 1 version instead of the 1 over n. That makes an unbiased estimate of sigma squared. And instead of using this normal distribution, which is based on a limiting argument, they say, well, actually, it turns out we know the exact distribution of this thing. It's not just asymptotically normal. We can actually work out what the distribution is of x bar minus theta naught root n over this sample standard deviation. And it has a distribution known as a t distribution. The t distribution with n minus degrees of freedom. So t distribution is something that looks a lot like a normal, but it is, yes?
Normal externally or in general?
No, for normals. This is only for normal data. Under this model, this has an exact distribution that we know. It's called the t distribution. Again, it looks a lot like a normal. It's got thicker tails. It was worked out. And who knows, who worked out this distribution? Student. That's why it's called the student t distribution. But who was student? There's no one named student. Well, America's a major student, but not involved in the student t-test. It was William Gossett. He worked at Guinness Breweries. He was doing tests for their, for their brewery and trying to brew good stout. They have great stout. But they had a company policy that their scientists could not publish under their own name. So he made up a pseudonym. He called himself Student. He published it under the name Student. So it's become known as the Student T-test. But we should really call it the Gaussian T-test. And it's pretty clever that he worked out the exact distribution of this. However, I'm a bit of an outlier here. So a lot of books will tell you you should use the student distribution to determine this cutoff value, not the normal. Now, I think using this t-distribution is actually a complete waste of time. Because first of all, once n is about 20, you can't tell the difference between a t-distribution and a normal anyway. And when n is small, the only way this is more accurate than the normal approximation is if the original model is exactly correct. It's only when the data are exactly normal that this has this t-distribution. The data are never exactly normal. So the idea that when n is small, that the t-distribution is going to be a better way to state this distribution than to just approximate it with a normal is pretty bogus, actually. In fact, if you have 5 observations, you shouldn't really be analyzing the data. You shouldn't be looking up the t-distribution. So you'll notice in my book, I do not put much emphasis on using the t-distribution. I think it's a waste of time. We should wipe it from all the curricula. The poor students, like in our first year's undergraduate classes, we make them learn all about t-distributions. It's just a complete waste of time. Boy, this is being recorded. Am I going to get... Make sure I censor this. Anyway, I wanted you to be aware of that because you'll hear people talking about t-tests and t-distributions and so on. But for any moderate sample size, we can just use the central limit theorem. This is approximately normal and just use the rule of thumb. So in this class, no t-distributions. Okay, so we'll do some more examples, in particular some vector valued examples in a minute. But now before we do that, I want to talk about how do we compute this cutoff in general, because the way we've done these examples is we wrote down the likelihood ratio statistic, then we kind of rearranged it to, by luck, it looked like something familiar, and then we were able to kind of deduce what the cutoff should be. But obviously that's not a very good general strategy. So there is a more general strategy. Which is the following thing. Actually, let's move this up a bit. So keep in mind our original picture. I've got some parameter space, this null. We'll think of as some, say, linear subspace of some different dimension. And we're computing this likelihood ratio statistic. And here's a very useful general result that, let me define D to be the dimension of the original parameter space. Now this subspace here has lower dimensions, so let's call that D0. And let's let the difference of those be K. If I take -2 times the logarithm of the likelihood ratio statistic, then we want to know its distribution under the null hypothesis. That's how we always get the cutoff values. Remember, under the null hypothesis, we want to make sure that the probability of rejecting is no more than alpha. So our first order of difference is what's the distribution of this under the null. So the distribution of this is a little bit hard to work with, so we just do a transformation -2 log. Turns out to make it a bit easier. Because under the null, this converges to a chi-squared distribution with k degrees of freedom. It has a known distribution. Let me remind you what a chi-squared is. If I take k independent standard normals, and if I square them and sum them, I get a new random variable. The distribution of that random variable is called the chi-squared k degrees of freedom. And in particular, so if I draw a picture of it, it's going to look something like this. There's our chi-square density, and there's going to be, again, a place where I can chop this off, and there'll be alpha probability here, so we'll call that chi-squared k alpha. So the idea here is this is minus, I'm going to reject when it's big, so you reject null. Minus 2 log lambda is bigger than this cutoff value. And under the null hypothesis, since this is the distribution of this, the probability of a false rejection is the probability here, which by construction is exactly alpha. This is the general procedure for doing a likelihood ratio test. You take minus 2 times the log likelihood. If it's bigger than this critical value, you reject the null hypothesis. Where do you get this critical value? Well, it's in every piece of statistical software. Will give you the quantiles of a chi-square distribution. All right, so we'll do a few examples in a minute. Let me just make sure the procedure, though, is clear. Any questions about that? Okay, so this is a number, and you have to look it up. This is something you compute from the data, and this is your rejection rule. Again, you can try to work out, in each case, an exact cutoff value without relying on large sample theory. And in principle, you can always do this numerically. But we often just do this because, now this is a quick, easy test. You compute the statistic, and this is the cutoff value. So it's just an approximation, but it's often a very accurate approximation. All right, so, and again, with scalars, you have the option to do the wall test or the likelihood ratio test. But we're going to show you some examples where we just do vectors, where you don't have the option. If it's truly a vector thing you're testing, then you're going to have to do the likelihood ratio test. Yeah.
Can we do this kind of test when data zero or like the null hypothesis is like actually the same dimension as the other one?
So the theorem I just gave you assumes that the null is a linear subspace of lower dimension. Now, if theta 0 is some full dimensional set in some weird shape, you can still do this test, but you can't use this theorem to compute the critical value. You're going to have to figure out some other way to make sure it has type 1 error. So let's actually, in fact, let's prove this theorem. I'll just do the one-dimensional case. So suppose we have a scalar parameter, and we choose to do the likelihood ratio test. I want to show you that minus 2 times the log likelihood ratio test goes to a chi-squared. It'll be just 1 degree of freedom. Because when you have a scalar parameter, so a real valued parameter, and I want to test that it's equal to a particular value theta 0, well, the full dimensional thing is one-dimensional. Under the null, the dimension is 0, right? It's just a single point. So the difference in dimension is 1. So for just doing a scalar parameter, we're going to show that that converges to a chi-squared of 1 degree of freedom. So let's actually prove that so you can see where this chi-squared comes from. So it won't seem mysterious. Right now, it's probably looking a bit mysterious. So we'll do our favorite trick. We're going to use Taylor series. So log likelihood based on n observations at theta. And what I'm going to do now, first of all, is approximate this with the Taylor series around the MLE. So that's going to be L of theta hat plus L prime theta hat. That's theta minus theta hat plus 1/2 squared. So you're going to stop there. This is just to get a useful expression for the log likelihood. Now, we should notice that this is the derivative of the log likelihood at the MLE, so this is 0. Okay. And what is the likelihood ratio test? Well, actually, I want the likelihood ratio, then I take the log. So that's the difference of the likelihood at theta hat and theta 0 times minus 2. So it's just the difference of log likelihoods. Okay, so minus 2 log lambda, therefore, is equal to 2 times L of theta hat minus 2. Say well, no, that's actually exact. Now approximately equal to. Now I'm going to use this expression up here. So what happens? Well, if I look at theta 0, let me put in theta 0 here. I'm going to get L of theta hat plus theta hat minus theta 0. When I take this difference, this first term is going to go. And so all I'm left with, and there's a 2 in front, that's why the 2 is there. We just are left with the second derivative of theta hat times this theta hat minus theta 0 squared. Okay, so I just remind ourselves this is from 10 observations. So I just took that, evaluated at theta 0, and then subtracted those two expressions. And now I'm just going to rewrite this as minus L double prime theta hat. I'm going to divide through by the Fisher information at theta 0 and multiply by the Fisher information at theta 0. And I'm going to rewrite this as root n squared. And what? I feel like I've lost an n. Like there's an n term. Where's the n? Oh, right. I think there's an n missing here. Let's put a minus here. Let's put a 1 over n here. That seems to be missing in the notes. Because I put an n here. That looks better to me. We're almost done. Because this is the log likelihood based on n observations. So that's the sum of the second derivative. The sum times 1 over n is the average. Minus the average is converging to its expected value, which is what? It's the Fisher information. So this top is converging in probability to I of theta 0. Actually, this should be, for that matter, I1. I feel like, let's keep going. There might be another typo here. I don't like the look of that. So this is going to 1 in probability. And this up. Now what's happening to this? So what are we getting? This is converging a distribution. I've got I. But what is, this is just the limiting distribution of the MLE. What is that? That's a normal. Remember, root n, theta hat minus theta 0, is converging to a normal, the variance 1 over I, or in other words, it's equal to 1 over root I, which is a standard normal. Okay, but we're squaring it. So it's z squared over I, which is z squared, and that's chi-squared 1. So there are a couple corrections in the notes. I see that I should have had a 1 over n, and these i's should be just Fisher information based on a single observation. How did that not get caught before? And that's it. And that's why minus 2 times log the likelihood ratio, minus 2 log likelihood ratio study converges to a chi-squared. And you can see by taking the log and minus 2, it makes it easier to get the limiting distribution. So on Wednesday, we'll do some more examples. I'm going to give back test 2. The median score was 79. and the quartiles are 72 and 89. So the test scores are quite high. And I'll do my, so as usual, I'll start the alphabet way over there and end the alphabet over here.